irreducible components in large tensor products of finite dimensional representations of simple algebras. So this is a continuation of this project, and now it's done with these three people: Anna Lachevska from Lausanne, Olga Postnova, and Dima Solovyev from St. Petersburg. So we did it for sl2, and so now it's sl3 time. So for any G, it's going to be a little bit more complicated, but it's sort of, I think the complication is in a controllable way, in the sense that if you really focus on this specific problem, it's probably doable. If you want to know everything about representation theory of these algebras at roots of unity, that can be complicated. Okay, so first let me say a few words about quantized neuroscience. So you see it's a continuation of the previous talk, so it's number 4. Quantized universal developing algebras. So we are focusing here on quantized sl2. And so if V is a generic, generic means that it's a variable, I should say, not generic, but it's a formal variable. So we consider the algebra over the field of rational fractions, rational functions in V, and the relations it's generated by Kf, by K invertible E and F, with these defining relations. I think many people know these relations. So it's important that now we consider V as a formal variable, not a number, and we work over this field. It's a Hopf algebra with this coproduct and with this co-unit. So then in rational functions in V, there is a subring. It's the ring of integer valued Laurent polynomials in V. So you can consider the universal developing algebra over this subring. And well, let's define an example of such subalgebra. So we consider so-called divided powers. Divided power of E, divided power of F, and we just define this subalgebra as the one generated by these divided powers. There are plenty of other elements in UV SL2 you can divide by anything, but we consider only those. And we consider, say, polynomials of these elements, modular whatever relations they satisfy, that will come later. And we consider these A linear combinations of such polynomials. So first claim that these funny elements, they belong to our algebra, simply because they appear as commutators of these divided powers. And then the relations were written by Lustig. So this is a complete list of relations in this algebra. I'll call it the algebra with divided powers. So it's these relations. Now I just want to emphasize that in this algebra, this ENF and FN, they are no longer divided powers. They're just generators. So here En, Fn are generators, and these are the relations. So, and it's Lustig showed that this So the difference, of course, is topological. I mean, if you specify V to some real number, then this algebra differs very little from the initial algebra, but for formal variable V, they are quite different. And they are very different when you specify V to a root of unity. So, let's choose Q to be this 2Lth root of unity. So we assume that L is odd, otherwise there is a technical complication, which is not serious, but just easier to deal with odd numbers here. So I assume that M and L are relatively prime. So L is odd, but it doesn't have to be prime. So Q to the L is -1, Q to the 2L is 1. This is exactly the kind of Q that appears in topological quantum field theory and in modular categories that sort of were used to construct topological quantum field theory. So then we define the algebra UQSL2, the algebra at roots of unity with divided powers, as this tensor product. So we take our algebra with divided powers with formal variable V, and then we take the tensor product over A with this field. So here A acts in the usual way by multiplication on UA-SL2, and it acts in this particular way. You specify V to Q on the right. And since there are no denominators, so I just want to emphasize that here there are no denominators vanishing when we specify V to a root of unity. So as a result, you get so-called big quantum group at roots of unity, or quantum group with divided powers. And there is a natural question: what is the representation theory of this algebra? So, so first, let's look at the structural theory. So there is this fact, again, that goes back to Lustig. So if you look at the, so let's suppose that M, so you write M modulo L. So it's M1 L plus M0. M0 is the remainder of the division of M by L. M1 is the integer part of this division, and M0 is the remainder. So the remainder is between 0 and L minus 1. So if you write M in this way, then the generator with the divided power M can be expressed in this way, where E is just the one that we had before, and E to the L is the divided power. If you write it as a divided power, then the denominator vanishes. So this is why it's important to have this particular algebra where there are no denominators that vanish, but the generator EL doesn't have a meaning in terms of small quantum SL2. So this is the theorem, and then the the next step of this theorem is that this big quantum group with divided power is generated by these elements, our old friend E, F, K, K inverse, and our new friends, the divided powers of E and F. And the relations between them, well, they follow immediately from the relations over here. Okay. So then the other fact is that K to the 2L is 1. in this algebra, so that k to the L is, and k to the L is central. And this algebra appears as a Hopf subalgebra. Okay. So, well, let me. For us, what's important now is just that it's a subalgebra. So now let's look at the while modules. So now let's look at representations, and let's so consider while modules. So these are the representations with the, well, I want to call it highest weight, but there is no Z grading, so you cannot say really which one is highest, which one is lowest. Instead, we will say that Wn is generated by F, by acting on F, on the vector X, on which K acts in this particular diagonal way, and which is annihilated by both E and divided power by L. So, and it's generated by from X by F all the way to Fm, where Fm is the divided power. So here M doesn't have to be between 0 and L minus 1. So it's, we will always write it modulo L. Okay, so then Anderson and Tugendhauer, they proved the following, that the modules, these while modules, are self-dual and simple, and it's simple only if and only if M is between 0 and L minus 2, or if M has this specific form. It's LM1 minus 1. M1 is an integer number. So then for each integer M, this while module has a unique simple quotient, subquotient module LM. So so this is actually a quotient model. So this is the short exact sequence that demonstrates this. And then the third statement is that this representation is isomorphic to the tensor product of vector spaces LM0, LM1, and the first space is a module over the small quantum group, an irreducible module over the small quantum group, where the divided powers act trivially. And the second module is where small quantum group act trivially, and the divided powers which generate the universal enveloping algebra of sl2, they act irreducibly. So it's, one can say that it's a tensor product of two irreducible representations. So now tilting modules. So here is a formal definition of tilting modules. It's the module that has a kind of two filtrations. One is by while modules, the other is by dual while modules. And it's a big theory and representation theory of algebras, a theory of tilting modules, and it turned out to be extremely useful for quantized universal enveloping algebras at roots of unity. So this is a formal definition. I will not review the whole theory of tilting modules. Just so what we need is some kind of simple facts tailored to quantized SL2. And so now the question is, say, let's take tilting module T1. It's two-dimensional. So there is no room for an action of divided powers, so they act trivially. So, so it's an irreducible module for UQSL2 and also for small UQSL2, only for E's and F's. So it's the old friend, it's the two-dimensional representation of small quantum group lifted to big quantum group. So now we will try to play the same game. We will look at the tensor powers of this two-dimensional representation. Remember, I started it with this last talk. So we looked at the tensor powers of two-dimensional representation of SL2. And these were the multiplicities of irreducible subrepresentations in C2 to the n for SL2. So I'll use these notations here and okay, and then the theorem is the following, that if n capital, if the degree of the tensor product is between 1 and L minus 1, then the tensor product decomposition is the same for as for SL2. So it's given by this formula. However, if L is greater or equal than L, and you see that the reason for this is very simple. In this tensor product, only irreducible representations with the weights between 1 and L minus 1 will appear. And the branching rules for these representations are the same as for SL2. So it doesn't matter. But then if n is greater than L, greater or equal than L, so then the more complicated tilting modules will appear. And the answer is the following. So I think I didn't give I'm sorry, I forgot to give a definition of tilting modules. So instead of the definition, I'll just say that tilting modules, well, they are parameterized for quantized for large quantized SL2. They are parameterized again by integers. Again, we will count them modulo L. It's very convenient. And well, they have certain so there are short exact sequences. Well, now they are not short now, but it's the filtration. So these modules are filtered by while modules and by dual while modules. Okay. So anyway, so they are parameterized by these integers. So what happened for large tensor products is that T1 to the power n again is a direct sum, is isomorphic to a direct sum of tilting modules with some multiplicities. In fact, it's a theorem that I should have mentioned here. Theorem tilting modules, they form a subcategory in the category of finite dimensional UQSL2 modules, in the category of finite dimensional UQSL2 modules, and this subcategory is monoidal. So it's not. Yeah, I saw a statement in the literature that it's not a braided monoidal subcategory. It's not necessarily braided monoidal subcategory. And then I also saw a statement in the literature that it can be fixed. So I don't know exactly the status of this. I didn't check neither of these statements, but it's definitely a monoidal subcategory. So since it's monoidal subcategory, we can, so we have this property. So the question is, what are the multiplicities? And it turns out that the multiplicities can be computed. This is one of our results. So they are given by, again, by these Catalan numbers, if L in this range, and they are these alternating sums of Catalan numbers otherwise. So now, okay, so remember that for SL2, we had the very simple tensor product rule that if you multiply an irreducible module VL by C2 by a two-dimensional module, it's isomorphic to the direct sum VL minus 1 and VL plus 1. And so you can think of this as some kind of combinatorially as about this decomposition as iteration of lattice path on a lattice. And then the formula for the Catalan number can be obtained by the reflection principle from the number of lattice paths of this type. And the number of paths of this type is given by binomial formula. That's a simple exercise. And that's why you have multiplicities counted by Catalan numbers. So that was nice for SL2. Well, unfortunately or fortunately, depends on the philosophical principles. So life is nice and easy, when everything is simple, but science is boring, and vice versa. Science is nice and interesting when something is complicated. But yeah, so we're talking about science. So here, fortunately, it's more interesting and more complicated for quantized SL2, but it's more interesting and more complicated in a reasonable way, so we can still handle it. So here is the tensor product rules. For small k, it's just the same as SL2. So we're approaching to the critical value L minus 1, still the same as for SL2. But this term kicks us out from the kind of SL2 range, as we will see. If we will take this representation multiplied by C2, we get the tilting module that is that consists of, so it's this tilting module where you have VL, VK. So it's this is the special one, but the structure of the tilting modules at the next level is this. Roughly speaking. So then the tensor product rules, you see, at these places, it's different from SL2. Then it goes kind of along as in SL2. So this is SL2. This is SL2. So then, again, something strange. And then it goes on as an SL2. So what are the lattice paths? Lattice paths in this case, here they are the same as for SL2. But then you see, you multiply VL minus 2 by C2, and then you get only one tilting representation, TL minus 1. So, so the path goes only in one direction. And then you multiply TL minus 1 with C2. Well, the path still goes in one direction. Yes. And then you do it next time, and then you have multiplicity 2 subrepresentations. And then this block gets repeated over here, and it gets periodically repeated. So it seems like it's a mess, but it's actually there are some patterns here. So this is kind of magnified picture of this. So this is where the small UQSL2 lives. So this whole lane is where tilting modules for large SL2 lives. So here the rules are the same as for SL2 inside of this blue parts. And then over here they are different, just as it's explained here. So in terms of lattice path, you get something like this. So you move only in one direction at certain areas. So here it's SL2 branching rules. And then this lattice path, they are allowed to jump back by 2L from these representations, from these places. Not actually from this place is too small, but from all these places over here. So that would be 4L minus 2, 5L minus 2, and so on. And so this is the kind of lattice path. So it's wandering as for SL2. Then at some point it reaches the this red spot. Then it can go only in one direction. There is no other choice. If it comes to this point, then it jumps to the other area. And then from this area, the path doesn't have an escape. It never goes back. It can jump into the next chamber and wander over there. But then, if it's lucky, it can hit this long jump point, and then it can jump back. So this is the structure of lattice path. And of course, this structure is quite complicated, but remarkably, it can be used for counting number of paths. So this is the work. Part of it was done separately by Postnova and Sl2. So then, well, you see, you have all these representations, tilting modules, and you know that a tilting module is, well, unfortunately, I'm sorry, I thought I wrote it, but I didn't. So there is only this statement, but there is a similar statement for the tilting module. That it's also a tensor product. So anyway, so if you look at this formula, you can see that you can define formally formal character of such representations. So formal character of V is just the sum over all weights of this module, some formal variable x, and then the dimension of this weight subspaces. It's just the same as in kind of representation theory of simple algebras, you can define formal characters that turn into kind of normal characters if you lift it to a group, but sometimes you cannot lift it to a group, so the kind of usual character as a trace of representation doesn't make sense, but you can still define for various purposes these formal characters. So this is what we do here. We define formal character exactly by that formula. So this is the definition. And actually, this is not only the definition, this is also the result of computation. So for representations, so this is the representations of SL2, UQ SL2. This is where representation theory is basically the same as in SL2. So this character is the same as SL2 character. For the next module, you use the tensor product formula, and you got this formula. And then for the next module, you get this. And then for all of them, you get this formula. So these are some formulae for some polynomials. And these polynomials, they satisfy the same multiplication rule. If you multiply any of these polynomials by x plus x inverse, you will reproduce these branching rules. So now we have characters. They are polynomials in formal variable x with integer non-negative coefficients. So we can now say that, let's assume that x is a positive number. And then these polynomials will be positive. And we can define the probability measure on not on irreducible components, but on on the set of tilting modules that appear in the nth tensor power of the two-dimensional representation. So this is a probability measure, and of course, if you're interested in this asymptotic representation theory, we want to know what happens as n goes to infinity. So there are several ways to approach to this problem. One way is to study the Markov process that approaches to this probability measure that correspond to this probability measure, and then study the asymptotical behavior of this Markov process as n goes to infinity. Well, the other way is just analyze combinatorially these properties, these numbers. So it's not impossible, and actually this is how it was done initially in our work, and then we realized that something better can be done. So what you can do is you can find polynomials which are orthogonal with respect to the usual SL2 measure on SL2 characters. So this is a totally formal game. So you have polynomials. They look like they are characters, but they are formal characters. So now let's play with them anyway as we would play with characters. Let's assume that X is on the torus, on the Cartan subgroup of compact of SU2. And then let's try to find, so now we know that these characters are not orthogonal, but still they form a basis in the space of polynomials, in the space of symmetric polynomials. In this case, symmetry is x to x inverse. Because they form a basis, maybe there is a reasonable orthogonal basis, orthogonal with respect to this scalar product. And it turns out that yes, one can find these orthogonal polynomials. They look like this, very reasonable polynomials. And then as a corollary of this, we can find the formula, the integral formula for these numbers. these complicated compositions of Catalan numbers. And for any G, I think there is a hope for this. These numbers are so-called Kazhdan-Lusztig coefficients of Kazhdan-Lusztig polynomials, dual Kazhdan-Lusztig polynomials, and so on. So maybe there is I think there is some kind of reasonable hope for general G. And then you have an integral, n goes to infinity. So we'll know that in this case you use the steepest descent method to compute the asymptotical behavior of the integral. And this is what we did. And this is the result that we got. That this probability measure, it converges to the tensor product of two probability measures. One is this very special probability measure on the small quantum group interval. So that's K0 between 0 and L minus 1. This is where the modular tensor category lives, and so on. So, and the other is in this range. So before I'll comment the formula, so this is what happens. So remember, I was explaining that once you switch on once you study the character probability measure, this number x, which is parameterized as e to the t, it gives the drift to this random walk, and the drift is determined by this parameter. And so here is the drift. So it crosses infinitely many of these walls, and then at the end it's distributed Gaussian in a Gaussian way between the walls. But then also microscopically there is a remainder. So you should somehow you still have this discrete component, and this discrete distribution is given by this formula. And the Gaussian distribution is the Gaussian distribution. And our probability measure converges to this tensor product of finite discrete probability measure, just collection of these numbers, and the Gaussian measure, continuous Gaussian measure on where the path ends. So this is the result. This is how we got it using the steepest descent. But also we checked it using the other method. So this is still work in progress, and the paper should appear. I mean, basically the work now is to write it down, and most of it is written, but still I think it will be only end finished in 2023. So this work is about UQ-SL2, the large quantum group, the big quantum group. The advantage of studying the big quantum group is because you can introduce this formal character, and so you have the character measure on these representations. And in other words, you have one parametric family of probabilistic measures, and you can see that the result is kind of entertaining. So if you study a small quantum group, there is no room for no continuous parameter x. So there are only two kinds of measures you can imagine. So let me first say a few words about the algebra. So here is the small quantum group. It's finite dimensional. E to the L, F to the L is 0, K to the 2L is 1. It's actually a subgroup. Subalgebra. So then you have irreducible representations of dimension 1 to L-1. You have this special so-called Steinberg module of dimension L. And then we have tilting modules of dimension 2L. So then, well, we constructed probabilistic measures in the last lecture in two ways, using characters and using dimensions. So now we have a choice of also quantum dimensions. But quantum dimensions, this is a little bit boring in the sense that it's just quantum dimensions are zeros for all tilting modules. This is why I didn't even discuss this for large quantum SL2. And they are still zero for tilting modules for small quantum group, except when the tilting module is an irreducible module. So it gives, so it's, I think it's well known that basically it counts the, yeah, you get this standard distribution at the end. It's distribution by quantum dimensions essentially. So so we've done this, but then you can use the usual Plancherel measure. So just the dimensions. So here quantum dimensions don't appear, but the nature of small quantum SL2 appears in the tensor product rules. So so these are the rules. I'm not going to write all of them. They follow immediately from the branching rules for large quantum group. So instead, I will draw a picture of these random walks. So it's similar to, well, it's not similar. It's actually quite interesting. So if we wouldn't have, if we would count only dimensions, that would be the lattice path that we count, and this would be the random walk that we have in kind of Markov process interpretation of all this. So but if we look at, if it's possible to go out, so this is the branching rule over here. So you can see that once you cross here, there is no escape. You wandering around here, and that's the idea that say if by any chance you consider not tensor products of two-dimensional representations, but say you start from this point, then you're wandering on this cylinder and you never go to the semi-simple part. And if you start from the semi-simple part, you cross to the cylinder, you move along the cylinder, you never go back. So so then you do the limiting measure, and the limiting measure, did I write it here? No. So it's the uniform here, and it's the same as for the quantum dimensions here. Well, and some numbers. Here. So this is so maybe sometimes next year I can give a more complete talk about this, and maybe by that time I'll say something about, at least about SL3. Okay, so so this is more or less all I wanted to say. So now some open questions. Say, suppose that you start from, I think I've said this last time, but I just want to repeat it. So suppose that you start with modular semi-simple, well, by definition, modular tensor categories are semi-simple. So you start with it, and can you extend it by tilting like objects? Do such extensions always exist? Well, we know it's true for U, Q, and G, but there are other modular tensor categories that come from subfactors, and I think this is not known in this case. So that would be
Okay, Nicolai, you disconnected just now, but did you unmute yourself? Let me.
yes, basically
Oh
I
yeah,
finished.
yeah.
I'm finished.
Okay.
I finished. Just for the completeness of the grand finale, I will switch on the yes. So I said that it would be interesting to see whether there are non-semi-simple extensions of categories, but in fact, it would be interesting to see if they exist at the level of Grothendieck rings, and then maybe get some interesting characters from there. Okay, so that's the end.
Okay. Thanks a lot.